Hello everybody, my name's eMoney SAD. Welcome back to my YouTube channel. Today we're going to go ahead and cover chapter 11. And chapter 11 is all about talking about synthesis. Now up to this point we have learned about how to work elimination reactions, substitution reactions, addition reactions. We've learned about so many reagents that when treated with this sort of starting material ends in this product, and so on and so forth. We have this really big toolbox of reagents and reaction patterns, and now we want to really put it all together because ultimately, organic chemistry is concerned with the construction of organic compounds from a specific precursor. The goal is to start with a precursor and then develop this ordered list of reagents that will transform your starting material into your desired product. And so here we really want to gain mastery of being able to determine the synthesis pathway, the list of reagents we would need to go from starting material to product. Now, we have seen one or two sequence problems like this these last few chapters from 7 through 10. Pretty much we've learned a bunch of these one or two sequence problems where you can start with a specific precursor and through a reagent or two transform it completely into some sort of desired product. And we've built this toolbox, especially these last 4 chapters we've covered, right? Some of those synthesis pathways we've already seen before were 1, 2, and very rarely multi-step, right? But we've seen them and we know that they require strategy to deduce. Now, in order to really get a good grasp of synthesis in general and learn to develop a strategy to tackle these problems, it is now more important than ever. It is critical to truly achieve mastery over all the reagents we've described in previous lectures and videos. All the reagents that we have learned, that we have discussed, that we have worked with from chapters 7 through 10 now up to this point are very important for us to remember and understand fully, because now at this point of organic chemistry we are really concerned with synthesis and synthesis pathways, and this will carry on, I promise, in organic chemistry too. So it's really good that you focus on remembering all the reagents that you've been given so far in OChem 1. They will carry into OChem 2. All right, so this chapter, this video specifically for me, I really wanted to focus and refresh your memory on all the stuff we've learned thus far, and really just to do practice problems while discussing important techniques. I mean, the best way to learn how to approach synthesis problems is just to tackle problems of various difficulty. All right, and that's exactly what we're going to do, but we're going to start by reviewing a few key concepts, and then we'll tackle all kinds of problems together, and we will continue even as we move into chapter 12 and 13, and then in all the organic chemistry 2 videos I also already have up, every chapter we cover will end with some sort of synthesis problem, because ultimately, now that we've introduced it, it will be the main focus, the underlying kind of objective of learning about functional groups and their reactions and preparations is to ultimately be able to use that knowledge of reagents, use that knowledge of preparation and reactions to then come up with very good synthesis pathways to get from starting material to end material. All right, so here's a really cool summary, right? Synthetically useful transformations. A lot of this is substitution and elimination reactions that we've covered in chapter 7. How to go from an alkyl halide. All right, you can replace that alkyl halide with an alcohol. We covered this. All right, and then to go back and forth between alcohols and tosylates. Remember, alcohols are not good leaving groups, but tosylates are. All right, how to go back from alcohol to alkyl halide, how to get a nitrile from an alkyl halide, how to get an ester from an alkyl halide. These are all the reagents you need to transform to and from alkyl halides, right? This was a foundational reagent list that we built in chapter 7. And this is working with primary substrates. You do kind of very similar things with tertiary substrates. And you can start with a tertiary alkyl halide and again do similar transformations to alcohols, to alkenes of various substitutions, and so on and so forth. So this is a very good summary list. Now also, if you remember from my chapter 7 videos, we really broke down some of the reagents that you need for all the transformations and key features of substitution and elimination reactions. Make sure you understand those. If you feel iffy, go back, reread the chapter, rewatch my videos, reach out to me, any or all of those. But just make sure that you are constantly trying to build your skills with reagents and what they do and how to move from starting material to certain end products. All right, now, this is these two graphs here, these two tables are summaries of chapter 8, where we learned addition reactions of alkenes. We covered every single one of these reactions, all 10 of them, in detail. We did practice problems. All right, I have a summary of these reactions and their requirements and things to keep in mind, like chiral centers or carbocation rearrangement, in chapter 8 notes. And also we started it with as a refresher in the chapter 9 notes. So if you want that table, you'll find it there. Right, so we learned how to start with a double bond, how to add things to it like halogens, or how to add alcohols and waters to the double bond, how to add molecular hydrogen to both sides of the double bond, halogens to both sides, alcohol groups and halogens to both sides. We learned various different reactions on how to deal with double bonds, and we carried the same sort of techniques straight into triple bonds, starting with a triple bond, how to add a halogen, hydrogen, alcohols, waters, all sorts of things. And we covered all 12 of these reactions in our chapter 9 video for this. So these tables are just good refreshers, especially if you feel like for the most part you have a general understanding, it makes sense how these works, but you just want things to quickly refresh your memories for chapter 7, 8, 9. These tables from David Klein textbook do a fantastic job, and I highly recommend really maybe sometimes taking a white pen maybe and just blocking out some of these reagents for yourself and trying to work them out yourself whenever you feel comfortable to do that. All right, so that's a good way to test your what you really know. Okay, now useful techniques, we're going to cover a few. All right, just again as refreshers. All right, how to do alkane transformation. So you start off with an unreactive alkane, some hydrocarbon chain of any length. This one's just 3 carbons. Right, you have this hydrocarbon. We know hydrocarbons are unreactive, so this alkane is unreactive. How do we work? How do we deal with an unreactive alkane if our end goal is to, for example, slap on an alcohol there or make a double bond? How do we do that kind of stuff if we're starting with an unreactive alkane? Well, this is where, again, you want to go back to all these reagents you've learned. How do you deal? How do you start off with an unreactive alkane? Well, you can always just add on some sort of functional group, and we know how to add halogens, right? We know how to add bromine specifically. You can use NBS, right? And then there you go. You've slapped on a bromine now. Now you have an alkyl halide, and we know exactly how to deal with alkyl halides because that is literally all of chapter 7, right? Taking alkyl halides and being able to do substitution and elimination reactions, right? So you could do a substitution reaction to substitute that halogen with an alcohol or whatever else, or you could do an elimination reaction, a nitrile. You could do, or you could do elimination reactions, remove that halogen, form a double bond. All right, so now that you have this alkyl halide, you can substitute alcohols, nitriles, whatever else you want here, or you could do elimination reactions. And then even with elimination reactions, you can go ahead and do an extra addition step to really add specific groups to specific locations. All right, so we've really learned a lot so far about how to do this kind of stuff step by step. Now the hard part is learning how to put all those steps together to come up with the appropriate synthesis pathway to go from starting material to end product. Because we've learned these step by step, but now we need to be able to put them together. Now another useful technique we've learned in our journey thus far is how to create and modify carbon bonds and skeletons. We learned that to create carbon-carbon bonds, alkylation of terminal alkenes is going to increase the size of a carbon skeleton. And if the size of a carbon skeleton decreases, then what we could take advantage of is a bond breaking reaction called bond cleavage. And we learned that when we covered ozonolysis here. So if our goal is to start with a small carbon chain and our end product is a much larger carbon chain, then obviously we have to create carbon bonds. And one way we know how to do this is alkylation of terminal alkenes. We covered this in chapter 9 of terminal alkenes. All right, and now if we've shortened our carbon skeleton, if we start from something like this and we want to end up with a product like this, what we can do is ozonolysis, where we cut that double bond right through the double bond and we slap oxygens as band-aids at the end. All right, another important thing to keep in mind, to remember with synthesis pathways, is that you can use alternating elimination and addition reaction steps to move functional groups. So if you start off with something like this and you want to end with this product, all right, you're starting off with having a leaving group potentially here, but you want to end up with a double bond, and that double bond is not near your leaving group, right? It's a little bit down forward, right? Here's our leaving group at this carbon. We want to end up with a double bond right here. The best way to approach this is to take advantage of the fact that you can alternate elimination and addition reaction steps to just move that double bond along your carbon skeleton. So we start off with this alcohol leaving group. We can do an elimination reaction, form a double bond here. Then we'll add something to the double bond. Okay, we've done an addition reaction. Now we can do one more elimination reactions to form ultimately a double bond at the position we want. So if you have a pi bond, okay, you start off with addition. If you have a leaving group, you start off with elimination. So if you're trying to move functionality, all right, whether it's a double bond or a leaving group, take advantage of the alternating addition elimination steps to accomplish that. And of course, we're going to take a look at that and see what that means in some practice problems. One last thing to note before we jump into a bunch of practice problems is sometimes if you're given a starting material and an end product and you're told to develop a synthesis pathway to go from starting material to end product and you don't know where to start, sometimes it's good to work backwards. Start from the products, all right, and work backwards to the precursors, all right? So do backward steps one at a time to help develop a synthesis pathway. This technique is especially important for complicated pathways, and it's actually known as retrosynthesis analysis. So if you're the one who prefers to work backwards, and actually that's sometimes recommended, even preferred, if you don't know how to get from starting material to end product, just go backwards from end product to starting material. And we'll see all of this, everything we've discussed here, all right? We're going to see every single thing here in some practice problems that we're going to do together right now. And we're going to start off easy, all right? We're going to start off with one-step synthesis. Here we want to identify the reagents that can be used to accomplish each of the transformations shown below. All right, we're starting off with this double bond. All right, this ring structure that has that double bond. And to this double bond, we're going to do a bunch of different things. We're going to add to the double bond a bromine and a hydrogen here. All right, we're going to add bromine on one side or bromine on the other side. All right, we might cut it up. Look at this. The ring is no longer a ring. It's a linear structure now, all right? What if we want to add alcohols to both sides? How are we going to do all of this? All right, so we're going to figure out the reagents. And these are just one-step synthesis, right? So this is just going to get us to, you know, be a little more comfortable with this and hopefully work up. All right, so we start off with one-step synthesis. This is pretty much all of chapter 8 here, all right? Because this is going to be addition reactions of alkenes. All right, just as a friendly reminder. And I thought this would be good because dealing with triple bonds, very similar to dealing with double bonds. So we might as well cover this. All right, so we're going to start off with 1 here. Let me get my highlighter. All right, we want to go from this double bond. All right, and we've added a hydrogen here and a bromine here to lose that double bond. All right, now the bromine is not going to the more substituted position, obviously. It's going to the less substituted position. So what we're doing here is we're doing halogenation, but anti-mark. So first thing we're doing here is halogenation through anti-mark addition, right? Because our bromine is going to the least substituted position. All right, the reagents we need for this are HBr, right? And to do the anti-mark version of this halogenation, we need peroxides. All right, that helps us do anti-mark halogenation. Now, if we look at 2, it's also halogenation. We add a hydrogen on one side and a bromine at the other, but this time it's mark addition. So halogenation, but mark addition. And so all we need is that HBr, no peroxides. Fantastic. Now, let's look at this third step here. Okay, so we're starting off with a ring structure, and it seems that we've opened up this ring structure. All right, and we know exactly how to do this. All right, and this is through using ozonolysis. We'll cut our double bond in half. All right, we preserve the 1, 2, 3, 4, 5, 6 carbon, 1, 2, 3, 4, 5, 6 carbon skeleton. We've preserved this, all right, but now it's open. All right, so we've cut right through this, and then we've added oxygens to the place that we've cut. All right, so that means that we're doing an ozonolysis reaction. All right, let's write this down, ozonolysis, and we know our reagents that we need for this, ozonolysis. I don't know how to spell that, don't come at me. All right, we need O3, ozone, all right, and then DMS. All right, those are our reagents for ozonolysis always. All right, fantastic. So that's 3. All right, what about 4? We want to go from this double bond. Now, we want to go from this double bond to 2 alcohols being added to both sides of the double bond. And look at those alcohols. All right, they're both on the same face. All right, so they're being added through syn addition. All right, both on the same face. So this is syn 4, right? We're doing syn dihydroxylation. Both alcohols are on the same face, all right? And so what did we need for something like this, adding 2 alcohols to the double bond, but where they're both on the same face? Well, we needed something like catalytic, oh, there we go, OSO4 and some NMO. All right, so those are the reagents we used for something like this. Now 5, if we look at 5, still adding alcohols, all right, but they're not on the same face. They're being added anti, not syn. All right, we know what this reaction is called. It's anti-dihydroxylation. All right, and the reagents we used for anti-dihydroxylation is COH and some strong acid. All right, and that's how we accomplished that. Fantastic. Let's look at 6 now. What is 6? What's happening at 6? All right, we're taking our double bond. We're adding an alcohol to one side and a bromine to another. All right, alcohol and bromine. That's a halogen. So this is a hydrogenation. All right, we learned about that, obviously. And the reagents we used for that, obviously, we needed halogen, so Br2, and then we need the alcohol, and we can do that through the form of water. So those are the reagents we need for hydrogenation. Fantastic. Now, if we look at 7 here, all right, 7, we're adding 2 bromines to the double bond. All right, so just plain old halogenation here. And we know that halogenation happens in the anti-fashion. So that's exactly what's occurring here. We're adding 2 halogens in an anti-fashion. And halogenation is pretty easy. Whatever halogen you're adding, you need 2 of them, obviously, right? So Br2 for this example. All right. Now, if we look at 8, what's happening at 8? Well, we have a double bond, and then suddenly we don't have a double bond. That means what we're adding here are 2 hydrogens. So this is hydrogenation, right? And all you need for this is molecular hydrogen, H2, but that can't work on its own. You need some sort of catalyst as well. Platinum is commonly used. You can also use something like palladium or nickel. That would work as well. Fantastic. Now, if we look at 9, all right, if we look at 9, what we have here is we've added an alcohol group, all right, to the least substituted side, and then a hydrogen on the other side. So we're adding alcohol to the least substituted side, and then hydrogen to the more substituted side. This is hydroboration oxidation. All right, so hydroboration oxidation. That's how we add water to the double bond. All right, and so the reagents for this are BH3 with THF. All right, then some H2O2 and sodium hydroxide. Now, if we look at 10, all right, if we look at 10, we've added an alcohol and a hydrogen again, but now the alcohol is in the more substituted position. All right, so this is just going to be a normal acid catalyzed hydration here. That would work for this reaction, and it's really easy because all you need is a strong acid of any sorts. So acid catalyzed hydration, all right, and obviously you need a strong acid. Fantastic. Now, this last part here, all right, 11 and 12. Let's look at 11 and 12 here. 11 and 12, sorry. Okay, we're starting off with a ring structure that has this one methyl group. And what we want to do is add a bromine to the more substituted position. So it's going to be that position, which is tertiary when dehydrogenated. So we want to add, essentially, that's besides the point actually. We just want to add a halogen to this position. All right, and we know that we can do this. We know we can do this, it's possible. All right, and there's really 2 ways to do this, but we're going to cover one right now. All right, to add halogen, right, to just a normal unreactive alkane, what you can do is treat it with Br2 and light. Right, so you can do this through a radical reaction, actually. Now, another way you can do this is also just to treat it with NBS, and that will also add a halogen at that position. Either or. And usually something to remember from, especially from multi-step synthesis pathways, when you get down to doing a synthesis pathway, sometimes there's going to be more than one way to accomplish the same thing. All right, and you just have to be able to figure out what you want to use, because there is more than one way to get usually from precursor to end material. All right, now these are 2 ways we can have done that. All right, now 12, our last and final step. All right, we're taking this alkyl halide now, right? Alkyl halide, and we want to form a double bond. Okay, we want to form a double bond. So now what we have to do is an elimination reaction. All right, and something that will accomplish this elimination reaction is something like, for example, sodium ethoxide will accomplish this. All right, and so this is how you can work through one-step synthesis. We've done all of this together already in great detail when we covered Chapter 8, addition reactions of alkenes, and we've also covered in Chapter 7 how to work with substitution and elimination reactions. All right, so this is a really good stepping stone if the idea of more than one-step synthesis is a little scary at first. Start off with just practicing one-step synthesis, all right? Take, for example, I'm going to scroll up. Take this graph, for example, study it, and when you feel confident, block out all of these and see if you, by yourself, can figure out what reagents you need to do all of these one-step synthesis. And do it the same for this. Do it the same for addition reactions of alkenes, and do it for addition reactions of alkynes. Practice these one-step synthesis first, a lot, more than one time, all right, constantly. And then when you feel like you've really gotten a good grasp of the reagents and what they do, then you can confidently move into more multi-step synthesis pathways. All right, because multi-step synthesis pathways require creativity, and they require that you have all the tools in your toolbox to be able to do them. And the tools in your toolbox are all of these sets of reagents that you should know. All right, so it's okay if you don't feel like you can just jump into multi-step synthesis yet. I mean, this is all new material. All right, you've probably never seen any of this organic chemistry material until you started this class. So obviously it takes a while to digest all of these reagents. So practice one-step synthesis first. All right, and then when confident enough, jump into multi-step synthesis. All right, so this was our first example of one step. Now we're going to move into more step synthesis problems. All right, and these two problems here that we're going to do require functional group transformations. I wanted to label it like that. We're going to learn how to get from starting material, precursor, to end product. We're going to do these problems together. Now we're going to talk through them, and hopefully, all right, you'll be able to see me implement some of those techniques we discussed in the first few minutes of this lecture, and you can see me put them to play for actual synthesis problems. Okay, so let's talk about this. All right, we're going to first begin by analyzing what we're given for the starting material and for the end product. So we're going to take a good look at these. All right, our starting material here has a 1, 2, 3, 4 carbon chain. All right, our end product here also has a 1, 2, 3, 4 carbon chain. So we're not necessarily growing our carbon chain here. But what you do notice is there is a difference in one thing that's very clear. In our starting material, we have a double bond here, all right? And at our end product, we actually have a triple bond there, okay? So we want to move from double bond to triple bond, all right? So this movement of pi bonds, right? We're not necessarily moving location of the pi bond, but we're transforming our pi bond. We're transforming our functional groups, if you will. All right, is going to require a few steps. It's not going to be straight from double bond to triple bond. What we can do here is add some functional groups to this double bond, all right, and try to transform it from what we know of having maybe leaving groups into a triple bond. One way we can do this is let's take our double bond that looks like this, all right, and let's transform it into, let's do an addition reaction where we add halogens to both sides of that double bond. All right, so let's use Br2 to go ahead and add bromine to both sides of this double bond. Like so. Now what we have are these two halogens, all right next to each other. All right, now if you remember, when we covered triple bonds, whenever you have either vicinal or geminal halogens, right? When you have either two halogens on the same carbon or two halogens only one carbon away, you can take advantage of that and convert it into a triple bond, all right, through the use of excess Na, NH2, and water. We covered this. This was one of the first things we've covered in chapter 9 when we started talking about addition reactions of alkenes, how to prepare triple bonds. Well, if you have two leaving groups, like two halogens, either on the same carbon or one carbon away, we can remove them, right? Some sort of double elimination reaction, if you will, to form a triple bond. And these are the reagents you need to accomplish that. All right. And so then what we form is that triple bond. Now, what you could have done here, another technique of how to approach this problem, all right, and we can erase these reagents just for 1 second. All right. Another way that would have been just as good, if not better, to do is you could have started with your end product and you're like, triple bond. How do I prepare a triple bond? All right. Well, we've covered this, right? You know you've covered how to prepare triple bonds. Well, we'll need two leaving groups that are either vicinal or geminal, all right? And that will lead you to a structure that looks like this, where instead of the triple bond, there were once two leaving groups, two halogens. And then you can ask, well, how did I get those two halogens there with from my starting material? Oh, I know how to do this. I can halogenate my double bond, and you would end up with the same result this way as well. So you can work from the start to the end, or you can work from the end to the start, whatever makes more sense to you. All right, fantastic. Now let's do B. All right, let's do B. Now we're going to take a good look at B. All right, we're starting off with this ring structure that has one carbon and a bromine. So we're starting off with an alkyl halide, all right, where the bromine is added to this carbon right here. All right, and we want to end up with a structure where the bromine is at the same location as this methyl group. So what we are doing here is moving that functional group. We're moving the bromine. All right. Now, the best way to do this, all right, is probably to do an elimination reaction first, all right, and then do an addition reaction to get there, right? Because one good way of moving functional groups, as well as moving pi bonds like we've talked about, is to take advantage of alternating elimination and addition reactions. So going back and forth to move things to different positions. So that's what we're going to try out here. All right, we're going to start off with this alkyl halide where the bromine is here. All right, and we want to move it. So first step is we're going to do an elimination reaction. We can use something like DBU or tert butoxide, whatever. And that's just going to do an elimination reaction at this position, obviously, because here's our leaving group. It'll come in, steal a hydrogen here. Hydrogen dumps its electrons to form a double bond. Bromine leaves, and boom. Now we have a double bond here. All right, now what we can do is do an addition reaction to this double bond. All right, where we add our hydrogen here and add our bromine here to lose the double bond. Now, we're adding the hydrogen to the least substituted position and the bromine to the more substituted position. So this hydrogenation has to occur through mark addition. So all we need for that is just HBr. And that will add the bromine here and break the double bond. And that's how you get this final product. All right, so far so good. We started with one-step synthesis. Now we're doing functional group transformations where we're moving leaving groups, we're moving pi bonds, taking advantage of alternating elimination addition reactions. And these are pretty easy. These are two-step synthesis pathways. All right, so we're slowly building our comfort and our techniques to be able to do harder and harder synthesis problems. All right, let's keep doing this. All right, let's keep practicing. We're going to do here, again, same thing. Let's develop synthesis pathways for these two reactions. Now, these reactions involve changes in carbon structure. All right, so we want to keep that in mind. So we're starting off here with a triple bond. So just 2 carbons here. And we're ending off with 1, 2, 3, 4, 5 carbons. All right, so we're starting with 2 carbons, ending up with 5 carbons. Now let's take a look further at our end product. We still preserve this triple bond. All right, we're still preserving the triple bond. We don't want to lose the triple bond ultimately. But what we're adding to one side is a methyl group, and we're adding this ethyl group to the other side of the triple bond. Well, it's a good thing that in chapter 9, we covered how to add variable groups, R groups, alkyl groups, to different sides of the triple bond. We know how to work with this. And so if we start off with a triple bond, all right, we can treat it with NaNH2 and then treat it with whatever alkyl group we want to add to it. So if we want to add that ethyl group, all right, we're just going to add ethyl iodide, for example, with some halogen. All right, and that's going to take this triple bond and add that ethyl group to it. Fantastic. Well, we're going to have to do this one more time because we want to add a methyl group to the other side. So again, same technique, NaNH2, and then the group we want to add, methyl iodide. All right, and that takes our triple bond now and adds a methyl group to the end. So whenever you have these terminal alkynes, all right, alkynes, right, you can add alkyl groups to the sides of this triple bond simply by using NaNH2 and then the R group you want to add, whether it's methyl, ethyl, butyl, whatever it may be, iodide. All right, and that's how you want to work this problem. Fantastic. All right, now let's do B together as well. All right. What do we have as our starting material? We have this alkyl halide to start off with, right? We have this benzene with this carbon bromine attached to it. Fantastic. What do we want to end off with? Well, we want to end off with this terminal alkyne. Terminal alkyne, this terminal triple bond. Okay, and also notice this is 1 carbon. This is 1, 2, 3 carbons, right? So we're obviously building our carbon structure here. Fantastic. So again, the starting material, benzyl bromide, different than the end product we have. Okay, so we're going to have to install 2 carbons here. Okay, now this is an alkylation process, and it actually can be achieved in just 1 step. All right, all you have to think about here is, all right, what if our starting material that looks like this, all right, Br, hey, this looks like something like an R group attached to a halogen, right? Something like this, all right? So what we can treat it with is the triple bond that we want to attach it to, a terminal one, all right, plus some sodium in there as a result. What this is going to do is it's going to react this here, like a little bit of a substitution reaction, all right? And we're going to get to replace that bromine, all right, with this triple bond here. All right, one-step synthesis here. All right, fantastic. Let's just keep doing more and more, okay, just to get comfortable. Let's do this, all right? Let's look at what we're starting off with. This is a 1, 2, 3, 4, 5 carbon chain. Fantastic. It's a 5 carbon chain. What are we ending up with? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've really grown this carbon chain. Now, it's a good thing. It's a good thing we're starting off with a terminal alkene, right? Because we can add things to this triple bond. All right, and what we want to add is 3 more carbons to that triple bond so we can get 8 carbon chain. Then we can worry about converting the triple bond to a double bond. All right, so then our first step has to be to grow that carbon chain. All right, because we need it to be 8, not 5. So we're going to do the same technique we just saw. All right, NaNH2, and then whatever we want to add. All right, a 3 carbon chain, 1, 2, 3, attached to iodide. All right, so this is the group we want to add to this terminal side of the triple bond. What do we get as a result? Well, we get something that looks like this. Fantastic. 1, 2, 3. Sorry, I almost missed a carbon there. Perfect. 1, 2, 3. All right, cool. Now, what you notice here, let's erase this really quickly, use a different color. All right, now to this double bond, we have 1, 2, 3 carbons on one side and 1, 2, 3 carbons on the other side. Let's look at this triple bond. We have 1, 2, 3 carbons on one side, 1, 2, 3 carbons on the other side. Fantastic. So we don't have to worry about shifting anything now. All we need is to convert the triple bond to a double bond. We know exactly how to do this, and we know how to do it to the point where this triple bond gets converted to a double bond that is obviously cis, okay? Not trans, but we need it to be cis. Both of the groups on the same side of the double bond, okay? We covered this in chapter 9. To convert a triple bond to a double bond in the cis conformation, what we need is molecular hydrogen. But we can't use our normal platinum catalyst. It's not going to give us cis conformation. We have to use a unique catalyst called Lindlar's catalyst. Right? We've covered this. This is going to take this triple bond, convert it to a double bond specifically in cis conformation. And that's how we get our end product. Now, I'm going to let you attempt C since I haven't given you any homework yet. Take an attempt at C. All right? Tell me what you think in the comments below, the set of reagents we would need to produce this end product from this precursor. All right? Now, we're still going to keep doing a few more. All right? Practice makes perfect, and that's exactly what you should be doing, especially if you've gotten to this chapter at this point. Highly recommend that you keep consistently doing synthesis problems, even if it's just 1 or 2 problems from your textbook every day. All right, do 1 or 2 problems. Check it with the solutions manual. If you don't have a solutions manual, damn, just email me and I'll check it for you. Okay, just make sure you consistently do practice problems. All right, so let's keep doing some more. Let's look at this. Here's our starting material, a good old triple bond. All right, and we want to end up with this molecule where there is an alcohol group and a bromine that we didn't have to begin with, and also absolutely no pi bonds. Okay, so quick thing, we have 1, 2 carbons here, we have 1, 2, 3, 4 carbons here. Okay, so before we even worry about these added groups, these bromine and alcohol, since we're starting with a triple bond, a terminal triple bond, let's take advantage of it and add that extra 2 carbons we need. That should be the first step since we are lucky enough to start off with a triple bond. All right, so we've done this enough times. We use NaNH2. All right, and we're going to add 2 carbons. All right, here's 2 carbons and iodide. So ethyl iodide. All right, what is this going to do? It's going to add 2 carbons to one side of this triple bond, I'm so sorry. Now what we can do is, well, we want to lose this triple bond, and then we want to add bromine and alcohol. So what we can do is we know how to add an alcohol and a halogen, right? Hydrogenation on a double bond. So what we can do is convert this triple bond to a double bond. All right. We can do this. We can, again, just use H2O and Lindlar's catalyst. We don't have to worry about cis or trans here, right? Because it's terminal, so it's just going to give us, boom, just a normal alkene. Now we know how to treat this alkene, all right, with halogen, right, Br2, and water, so we can add that alcohol group, all right? And ta-da, we have added our bromine and alcohol through the hydrohalogenation of this alkene. All right, so this synthesis pathway was just a little more involved, right? So you see how we're building up our confidence to do these. We did 1 step, then we did a few 2-step, and now this is 3 steps. All right, we're getting there slowly but surely. All right, let's do one more. We'll do C together, and I'll leave E for you to figure out. All right, so let's do C together. Let's do it in a different color. All right, what are we starting off with? Well, we're starting off with this carbon chain that has 2 bromines on the same carbon here and 2 methyls on this carbon. All right, what we want to end up with is a carbonyl here. Okay, fantastic. Now, let's think. All right, so our product is this methyl ketone. All right, we've seen this methyl ketone before. We know how to make this methyl ketone from a triple bond. All right, so if we had something like a triple bond like this that looked exactly, had the same carbon structure as our starting material, but without the bromines there, no, but instead a triple bond there. If we had this, we know how to get to a methyl ketone. We saw this in chapter 9. All right, it's just kind of like a acid catalyzed hydration. All right, doing an acid catalyzed hydration of this triple bond will give us a methyl ketone. Okay, but now the question is, well, how do we get from this to a triple bond? Well, guess what? That's how we prepare triple bonds. Whenever we have 2 leaving groups, like 2 bromines, either on the same carbon or 1 carbon apart, we can take advantage of that to form the triple bond. So that's exactly what we're going to do. We're going to start off. All right, we're going to start off with what we're given. Perfect, we have 2 leaving groups. All right, that means we could take advantage of our alkene preparation methods. We just need excess NH2 and water. This will do those 2 elimination steps we need to get a triple bond there. And now that we have this triple bond, like we just said, we know how to get a methyl ketone from this. All right, we need acid catalyzed hydration. That means we need sulfuric acid, water, and this mercury sulfate complex. And we can take that triple bond, all right, and convert it into this methyl ketone. And that is the synthesis pathway for obtaining that. All right, I'm going to leave E for you to accomplish. We've done so many synthesis problems together now. 1 step, 2 step, 3 step. We've really built up our confidence while refreshing our memory of all the reagents we've learned so far in our OChem journey. I hope this was helpful. I hope you continue to do practice problems. If you have any questions or if you need motivation or whatever else, feel free to reach out to me. I like to make myself available to you because I really want you to succeed in this course. But other than that, good luck, happy studying, have a beautiful day.